Look at any photograph of the night sky, one of those deep exposures where the darkness itself seems to sweat light, and you are seeing a lie. Not the kind of lie told with intent, but the more dangerous kind, the lie that arises from the sheer incapacity of your eyes to process what is actually there. Every point of light looks the same. A star in our own galaxy, a few hundred light years away, presents itself as a white dot. A quasar burning at the edge of observable space, 12 billion light years distant, shining with the combined fury of 500 trillion suns, also presents itself as a white dot. The universe does not label its monsters. It leaves them sitting in the archive, filed under probably a star, waiting for someone to notice that something is wrong. For 43 years, something was very wrong with an object catalogued as J0529-4351. It sat in the data like a splinter, under the skin of astronomy, not quite painful enough to demand attention, not quite smooth enough to forget entirely. Generations of telescopes photographed it. Automated classification systems sorted it. Graduate students scrolled past it on their screens without a second thought. The object was bright, yes, but bright in the way a nearby star is bright, which is to say bright in the boring way, the way that does not warrant a second look. And so it waited, burning with an intensity that would humble every star in the Milky Way combined, while the astronomical community collectively shrugged and moved on. What finally emerged from that waiting in February of 2024 was a discovery that recalibrated our understanding of violence at cosmic scales. The most luminous object ever detected in the universe, a black hole devouring one sun per day, an accretion disk spanning 7 light years, a distance so vast that light itself would need 7 years to cross from one edge to the other. The most violent place we know of in all of existence. And it was hiding in plain sight the entire time. If these long journeys through the strange help you drift or think or simply stare at something larger than yourself, consider tapping that like and subscribe button. It costs nothing and ensures these expeditions continue. Now, let us begin. The year is 1980. The place is La Silla Observatory in Chile, perched on a mountain in the southern Atacama Desert, one of the driest landscapes on Earth. The air here is so thin and so still that astronomers sometimes forget to breathe normally, their lungs working harder than expected at 2,400 meters above sea level. The sky overhead is not the sky you know. It is a different sky entirely, the kind of sky that urban humans never see, where the Milky Way is not a faint smudge, but a river of structured light dense enough to cast shadows. Inside the dome of the ESO Schmidt telescope, a photographic plate is being exposed. This is before digital sensors, before CCDs, before the explosion of computational astronomy that would define the next 40 years. The image forming on this plate is chemical, silver halide crystals darkening in response to photons that have travelled unimaginable distances to reach this mountaintop in Chile. The exposure takes hours. The tracking motors hum. The dome creaks occasionally as it compensates for Earth's rotation, keeping the telescope pointed at the same patch of southern sky. When the plate is developed, it will show thousands of points of light. Each one represents a decision the universe made billions of years ago about where to place its fire. Some of these points are stars in our own galaxy, relatively nearby in cosmic terms, perhaps a few hundred or a few thousand light years away. Some are much farther. Some are so far that the light now striking this photographic plate began its journey when Earth was still a molten ball of rock without oceans, without atmosphere, without the faintest whisper of life. The Schmidt telescope does not know this. The telescope does not know anything. It is a tube of metal and glass pointed at infinity, collecting whatever photons happen to fall into its aperture. The work of knowing comes later, when human beings examine the plates and try to make sense of the spray of light captured there. One particular point on this plate, in a region of sky near the constellation Pictor, glows with unremarkable steadiness. It is bright, yes, but not unusually so for a star. Its colour is perhaps slightly off, carrying a hint of blue that suggests either a hot young star or something else entirely. But something else entirely is a category that requires effort to investigate, and effort is a finite resource in astronomy as in everything else. The default assumption, when you see a bright point of light, is that it is a star, so the point of light receives a designation. It becomes part of a catalogue. It joins the vast filing system of the southern sky, one more entry among millions, waiting for someone to care enough to look closer. No one does. Not that year, not the next year, not for 4 decades. To understand why this happened, you need to understand how astronomers think about brightness. When you look at the night sky with your naked eye, all stars appear more or less equally distant. They seem painted on a dome at some undefined faraway distance, all of them roughly the same size, differing only in how much they twinkle. This is, of course, completely wrong. The stars you see span a range of distances so vast that the word vast loses all meaning. Some are a handful of light years away, some are thousands. The reason they appear similar in brightness is that the nearby stars tend to be dim intrinsically, while the distant stars bright enough to see tend to be massive and luminous. This creates an ambiguity that has haunted astronomy since Galileo first pointed a telescope at the heavens. A dim nearby object and a bright distant object can appear identical. The only way to tell them apart is to measure something other than brightness, some property that reveals the true nature of the source. For quasars, the critical property is redshift. When light travels across billions of years of expanding space, something strange happens to it. The wavelength of the light stretches. Colours shift toward the red end of the spectrum. The faster space is expanding between you and the source, the more the light stretches. And because the expansion rate of space increases with distance, redshift becomes a cosmic ruler. Measure how much the light has reddened, and you know how far it has travelled. But measuring redshift requires spectroscopy. You cannot simply look at a point of light and know its redshift. You must spread that light out into its component wavelengths, examine the resulting spectrum, identify the telltale absorption and emission lines that reveal the object's chemistry, and then measure how far those lines have shifted from their laboratory positions. This takes time. This takes telescope access. This takes the decision to point your instrument at one object rather than another. And when you have millions of objects in your catalogue and limited telescope time, you make assumptions. You triage. You say, this one looks like a star, so we will treat it like a star and move on to the more interesting targets. J0529-4351 looked like a star. It was bright. It was point-like. It did not vary dramatically in brightness in ways that would demand attention. Every piece of surface evidence suggested a nearby stellar object, perhaps a few hundred light years away, doing nothing particularly remarkable. The automated classification systems that began processing these catalogues in the 1990s and 2000s were trained on exactly this logic. Bright plus point-like equals star. Move on. The universe had played a perfect trick by making this object so impossibly luminous, so far beyond the scale of anything astronomers expected. It had guaranteed its own misclassification. It was simply too bright to be what it was. The algorithms looked at it and said, nothing can be this luminous and this far away. Therefore, it must be nearby and ordinary. They were wrong. Fast forward to the 2010s, the European Space Agency launches Gaia, one of the most ambitious astronomical missions ever conceived. Gaia's job is to measure the positions and motions of more than 1 billion stars in our galaxy with unprecedented precision. It creates a 3-dimensional map of the Milky Way, tracking how stars move through space, how far away they are, how fast they orbit the galactic centre. Gaia is extraordinarily good at what it does. It measures stellar positions to within a few millionths of an arc-second, a precision so absurd that it can detect the wobble of a star caused by orbiting planets from hundreds of light years away. The mission has revolutionized our understanding of galactic structure, stellar evolution, and the history of our cosmic neighborhood. But Gaia has a blind spot. When Gaia looks at an object and tries to determine whether it is a star in our galaxy, or something else entirely, it relies on certain assumptions. One of those assumptions is that truly distant objects at cosmological scales, should appear faint. Quasars billions of light years away should be dim points requiring careful observation to detect. If something appears bright, Gaia assumes it must be nearby. J0529-4351 appeared bright, very bright, 16th magnitude, which sounds dim to a non-astronomer but is actually conspicuously luminous for an object in the southern sky. Gaia's systems flagged it as a star. Not a particularly interesting star, just another point of light in the vast census of the Milky Way. It received a Gaia designation. It was added to the stellar database, and once again, the most luminous object in the known universe slipped through the net. This is not a failure of technology. Gaia worked exactly as designed. The failure, if we can call it that, is a failure of imagination. The algorithms were built to recognise things that fit within expected parameters. J0529-4351 did not fit. It exceeded every parameter so dramatically that it looped back around to appearing ordinary. Think of it this way. Imagine you're a security guard at a museum, and your job is to watch for thieves. You have been trained to look for suspicious behaviour, people lingering too long near valuable pieces, nervous glances, concealed tools. Now imagine a thief walks in wearing the uniform of the museum director, greets you by name and strolls past with absolute confidence. Your training tells you to watch for people who don't belong. This person appears to belong completely. You wave them through. The quasar walked past every checkpoint we had built. It was so far outside the expected range that it registered as unremarkable. The change begins in 2023. Christian Wolfe is an astronomer at the Australian National University, part of a team searching for bright quasars in the southern sky. Quasar hunting is a specific discipline within astronomy, requiring a combination of careful data mining and opportunistic observation. You start with catalogues, enormous databases of objects recorded by surveys like Gaia and the SO Schmidt plates. You look for objects that might be quasars based on their colours, their variability, their positions relative to known galaxies, and then you obtain spectra. The spectrum is the fingerprint. Get a good spectrum, and you know exactly what you're looking at. Wolfe and his colleagues had developed techniques for identifying quasar candidates that might have been missed by automated classification. They knew that the brightest quasars were the most likely to be misclassified, precisely because their brightness made them look like stars. They built algorithms specifically designed to catch these cosmic imposters. When they ran their analysis on southern sky data, J0529-4351 appeared on the list. It was flagged as a quasar candidate despite decades of classification as a star. Something in the colour data, perhaps a subtle signature in the way the object scattered light across different wavelengths, suggested that this was not a nearby stellar object. It might be something much farther away. It might be something extraordinary. On a night in late 2022 or early 2023, the team pointed the 2.3-metre telescope at Siding Spring Observatory in Australia at this candidate. The Australian night was clear, the seeing was good, and the spectrograph began collecting photons. When the data came back, everything changed. The spectrum showed unmistakable quasar features, broad emission lines from hydrogen and carbon, Doppler shifted by the object's violent internal motions superimposed on a continuum that spoke of thermal radiation from an accretion disk heated to billions of degrees. And the redshift, when they measured it, came out to approximately 3.9. Let that number settle for a moment. A redshift of 3.9 means the light from this object has been stretched by almost a factor of 5 since it left its source. It means the object is so far away that the light now reaching us began its journey when the universe was less than 2 billion years old, about 12 billion years ago. It means we are looking back in time, across almost the entire history of the cosmos, to see this object as it was when galaxies were still young, and the first great structures were only beginning to coalesce from the primordial fog. And at that distance, to appear as bright as it does in our sky, the object must be luminous beyond anything ever recorded. The team calculated the numbers. They checked them again. They brought in colleagues to verify. The object, now known as J0529-4351, shines more than 500 trillion times brighter than our Sun. Stop and feel the weight of that. 500 trillion is not a number the human mind can process directly. We have no intuitive sense for quantities that large. So let me try to give you something to hold on to. Our Sun is an ordinary star, middle-aged, middle-sized, burning hydrogen into helium at a rate that releases about 400 trillion watts of power every second. This is enough energy to vaporize the Earth many times over every second. It is enough energy that if you could somehow harness the total output of the Sun for 1 second, you would have more energy than human civilization has used in its entire history. Now multiply that by 500 trillion. The result is a number so large that it stops being a number and becomes a kind of violence. J0529 J0529-4351 is releasing energy at a rate that exceeds the combined output of every star in the Milky Way galaxy. Our galaxy contains somewhere between 100 billion and 400 billion stars. Add up all of their light, all of their heat, all of their radiation, and you still fall short of this single object. All of that power is coming from a region smaller than our solar system. The engine driving this output is not nuclear fusion, the process that powers stars. It is something more fundamental, more efficient, and more terrifying. It is gravity. At the center of quasar J0529-4351 sits a black hole with a mass of 17 billion suns. Here is how you should picture this, though the picture will break down at every level of examination. Imagine the Sun, our Sun, reduced to an object roughly 6 kilometers across. That is what a sun-mass black hole would look like. The matter has been compressed past all limits, past the point where atomic structure can survive, past the point where even quarks and gluons can maintain their identity. What remains is pure space-time distortion, a region where the curvature of space has become so extreme that nothing, not light, not matter, not information of any kind, can escape. Now, imagine that 6-kilometer object scaled up to contain 17 billion solar masses. The black hole at the heart of J0529-4351 has an event horizon, the boundary of no return, that stretches across a region comparable in size to the orbit of Neptune around our Sun. This is roughly 30 astronomical units, 30 times the distance from Earth to the Sun. If you place this black hole at the centre of our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune would all be inside the event horizon. They would simply cease to exist in any meaningful sense, absorbed into the singularity, their matter and energy added to the already incomprehensible mass of the whole. But the black hole itself does not shine. Black holes, by definition, do not emit light. What shines is the material falling into the black hole, the accretion disk that surrounds it like a ring of fire around a drain. The physics of accretion is brutal in its simplicity. Material falls toward the black hole. As it falls, it accelerates. As it accelerates, it collides with other infalling material. These collisions convert kinetic energy into heat. The heat becomes so intense that the material begins to glow, first in infrared, then in visible light, then in ultraviolet, then in X-rays. By the time the material reaches the innermost stable orbit around the black hole, it has been heated to temperatures of millions of degrees, and then it falls through the event horizon and is gone. This process, the conversion of gravitational potential energy into radiation, through friction and heating in an accretion disk, is the most efficient energy production mechanism known to physics. It is roughly 40 times more efficient than nuclear fusion. A kilogram of matter falling into a black hole releases more energy than a kilogram of hydrogen fusing into helium by a factor of tens. J0529-4351 is converting mass into energy at a rate of approximately 1 solar mass per day. Let me try once more to give you a feel for that. The Sun, our Sun, has been burning for about 4.6 billion years. Over that entire span of time, it has converted roughly 4% of its mass into energy through nuclear fusion. Most of the Sun's original material is still there, still hydrogen, waiting to be burned over the next several billion years before the fuel runs out. The black hole at the centre of J0529-4351 is consuming 1 sun per day. Not 1% of a sun, not 1,000th, 1 complete solar mass every single day, sucked through the event horizon and added to the black hole's bulk. The energy released by this process is what makes the quasar shine with the light of 500 trillion suns. This rate of consumption is so extreme that astronomers have given it a special name. They call it super-Eddington accretion, a state where the black hole is feeding so voraciously that it exceeds theoretical limits on how quickly a black hole should be able to grow. Under normal circumstances, there is a balance between the outward pressure of radiation from the accretion disk and the inward pull of gravity. If a black hole tries to eat too fast, the radiation pressure should push the infalling material away, creating a natural throttle on the feeding rate. J0529-4351 appears to be ignoring this limit. The accretion rate is so high and the luminosity so extreme that the standard physics of accretion break down. Something unusual is happening in the environment around this black hole, some configuration of magnetic fields or gas dynamics or geometric structure that allows material to plunge inward faster than theory predicts. This is an active area of research. No one fully understands how J0529-4351 is doing what it is doing. What we know is that it is doing it, and it has been doing it, presumably, for millions or billions of years. The accretion disk surrounding this black hole is the largest single structure of its type ever observed. When the ESO's Very Large Telescope in Chile turned its full suite of instruments toward J0529-4351 in 2023, researchers were able to measure the physical extent of the disk for the first time. The technique is called reverberation mapping, and it works by tracking how light echoes through the disk. When the central engine brightens or dims, that change propagates outward through the disk at the speed of light. By measuring the time delays between brightness changes at different wavelengths, you can infer how large the disk must be. The answer came back as 7 light-years in diameter. Stop and feel the weight of that. Our entire solar system, from the Sun out past the orbit of Neptune, spans about 8 light hours. Light leaving the Sun takes roughly 4 hours to reach Neptune. The entire system, everything we think of as our cosmic neighbourhood, fits comfortably within a region of space that light can cross in less than a single day. The accretion disk of J0529-4351 is so large that light needs 7 years to cross it. This is a disk of superheated plasma, billions of degrees at its innermost edge, swirling around a gravitational puncture in space-time, and it stretches across a volume that would contain over 15,000 copies of our solar system stacked edge to edge. If you could somehow stand at the outer edge of this disk, presuming you could survive temperatures that would instantly vaporize any known form of matter, and look toward the centre, you would see nothing but a wall of fire stretching across the sky, curving away in both directions toward an impossibly distant centre where the black hole lurked. Christian Wolff, the lead author on the Nature Astronomy paper that announced this discovery, was asked to describe the environment around J0529-4351. His answer was blunt. This quasar is the most violent place that we know in the universe. Violence is an interesting word to apply to an astronomical object. We think of violence as something immediate, something that happens quickly, something with victims and perpetrators. A car crash is violent, a hurricane is violent, an explosion is violent. These are events that unfold on human timescales, seconds or minutes or hours, and they involve forces that our bodies can recognize as dangerous even if we cannot survive them. The violence of J0529-4351 operates on a different scale entirely. Consider what is happening at the inner edge of that accretion disk, where material is about to fall through the event horizon. The gas there is not gas in any sense you would recognize. It has been heated past the point where electrons can remain bound to atoms. It is plasma, a soup of protons and electrons and ions, moving at significant fractions of the speed of light, twisted into helical spirals by magnetic fields stronger than anything we can produce on Earth. The temperatures in this region exceed 100 million degrees Kelvin. This is hotter than the core of our Sun by a factor of 10. Matter in this state does not behave like matter you know. It screams with radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. It shears and tears itself apart, with turbulent eddies forming and dissipating faster than light can escape from the region. And at the very edge, at the event horizon itself, physics as we understand it breaks down entirely. The curvature of space-time becomes infinite at the singularity. Time, from the perspective of an infalling observer, slows to a crawl and then stops. From the perspective of an outside observer, an object falling into the black hole never actually crosses the horizon. It simply redshifts into invisibility, its light stretched to ever longer wavelengths until it fades from view entirely. All of this is happening continuously, ceaselessly, on a scale that defies language. 1 solar mass per day, every day, for millions of years. The violence is not an event, it is a state of being. It is the default condition of the environment around J0529-4351. And we were looking at it for 43 years without realizing what we were seeing. There is something deeply unsettling about discoveries like this. We like to believe that our understanding of the universe is gradually expanding, that the blank spaces on the map are being filled in, that the territory of the unknown is shrinking year by year. And in many ways this is true. We know vastly more about the cosmos than we did a century ago or even a decade ago. Our telescopes are more powerful, our instruments are more sensitive, our computing systems can process data at rates that would have seemed like magic to astronomers of previous generations. But J0529-4351 suggests that the unknown is not just out there, waiting to be discovered in some distant and difficult-to-reach region of space. The unknown is here, in data we have already collected, in photographs we have already taken, hiding in plain sight because we did not know what to look for. What else is sitting in the archives? What other monsters have we catalogued and filed away, misidentified as ordinary stars, waiting for someone to realise that something is wrong? The astronomical community has begun to grapple with this question in earnest. There are likely other bright quasars lurking in southern sky catalogues, objects that appeared too luminous to be what they are, and were therefore classified as nearby stars. The discovery of J0529-4351 has prompted a systematic re-examination of these catalogues, using the same techniques that Wolf and his team developed to catch this particular cosmic imposter. We may be on the verge of discovering an entire population of these extreme objects, quasars so bright that they broke our classification systems, hiding in the data all along. But there is another question, perhaps more profound, that this discovery raises. If J0529-4351 is as luminous as it appears, and if that luminosity requires a black hole of 17 billion solar masses devouring one sun per day, then how did such a black hole come to exist? The light we are seeing left J0529-4351 approximately 12 billion years ago. At that time, the universe itself was less than 2 billion years old. This is very early in cosmic history, an era when the first galaxies were still assembling from clouds of primordial gas, when the first stars were igniting and dying and scattering heavy elements into space. Building a 17 billion solar mass black hole in less than 2 billion years is not supposed to be easy. Standard models of black hole formation start with stellar collapse. A massive star, perhaps 50 or 100 times the mass of the Sun, exhausts its nuclear fuel and implodes. The core collapses into a black hole with a mass of a few solar masses to a few tens of solar masses. This is how we believe most stellar mass black holes form, the kind we detect through gravitational waves when they merge. But getting from a few solar masses to 17 billion solar masses requires growth. The black hole must accrete material, must consume gas and dust and stars, must somehow multiply its mass by a factor of billions in less than 2 billion years. The mathematics of this are challenging. Even at the theoretical maximum accretion rate, the Eddington limit, a black hole can only double its mass every few tens of millions of years. Starting from a stellar mass black hole, reaching 17 billion solar masses would require more doublings than the age of the early universe allows. This is called the seed problem. Where did the first supermassive black holes come from? How did they grow so large so fast? Did they start as massive seeds? Perhaps hundreds or thousands of solar masses, formed from direct collapse of primordial gas clouds without ever becoming stars? Did they merge with other black holes, combining their masses in violent collisions? Did they accrete faster than the Eddington limit predicts, through some mechanism we do not yet understand? J0529-4351 is not just the most luminous object ever discovered. It is a window into one of the deepest mysteries in astrophysics, the origin of supermassive black holes in the early universe. Here is what we know. The universe, as we observe it today, contains supermassive black holes at the centre of virtually every large galaxy. Our own Milky Way has one, called Sagittarius A, with a mass of about 4 million suns. It is quiet now, dormant, not actively feeding, surrounded by a sparse population of old stars that orbit it like moths around a covered flame. But in the early universe, many of these black holes were active, they were feeding, they were shining, they were quasars. The epoch of quasar activity peaked when the universe was roughly 2 to 3 billion years old. This was a time of cosmic upheaval, when galaxies were merging frequently, when gas was abundant and readily available to fall into central black holes, when the universe was denser and more chaotic than it is today. Most of the quasars we observe are from this era, their light having travelled billions of years to reach us. J0529-4351 is from even earlier. It is from a time when the universe was less than 2 billion years old, before the peak of quasar activity, during the phase when the first monster black holes were still assembling. Studying this object is like studying a fossil from the earliest era of cosmic paleontology. It tells us what conditions were like when supermassive black holes were young, when they were growing at rates we struggle to explain, when the violence at the heart of galaxies was at its most extreme. And it tells us that even in this early chaotic era, nature was capable of building engines of destruction on a scale that humbles everything we know. The light from J0529-4351 takes 12 billion years to reach us. 12 billion years ago, the sun did not exist. The Earth did not exist. The atoms that now make up your body were scattered across the galaxy, locked in ancient stars that had not yet exploded, waiting for supernovae that would not occur for billions of years. The Milky Way was a younger, smaller galaxy, perhaps still assembling from the merger of smaller dwarf galaxies, its central black hole a fraction of its current mass. And somewhere in the southern sky, in a direction we now associate with the constellation Pictor, a quasar was already burning. It was burning then. It may still be burning now. We have no way to know. The light we see shows us the past, not the present. The quasar as it exists today, in the moment you are reading or listening to these words, is completely unknowable to us. Its present-day light is still in transit, still crossing the expanding gulf of space that separates us from that distant source. It will not arrive for another 12 billion years, long after our sun has exhausted its fuel and expanded into a red giant, long after the Earth has been consumed or ejected, long after anything recognizable as human civilization has ended or transformed beyond recognition. We are ghosts to that quasar as much as it is a ghost to us. The universe does not permit simultaneity across these distances. We are separated not just by space but by time, watching ancient fire from a dead epoch, reading messages that were sent before the Earth existed and will not be answered before the sun dies. This is the condition of cosmology. We study corpses, we reconstruct history, we peer into the past and try to imagine what the present might look like in regions of space where our conception of the present has no physical meaning. J0529-4351 may no longer exist in any meaningful sense. It may have shut down billions of years ago, its central black hole having exhausted the supply of infalling gas, its accretion disk faded to cold darkness, or it may have grown even larger, consuming its host galaxy, merging with other black holes, becoming something even more monstrous than what we observe. We will never know. Not really. Not in the way we can know things that happen nearby. All we have is the light, and the light tells us what was, not what is. Let the strangeness of that settle for a moment. Every telescope image, every quasar spectrum, every measurement of redshift and luminosity is a forensic analysis of the ancient dead. The objects we study are not objects in the present tense. They are memories, locked into photons, travelling across void after void until they happen to strike a detector, mounted on a mountain in Chile or a satellite in orbit around Earth. The universe is a history book written in light, and J0529-4351 is one of its most extreme chapters. In the next part of this journey, we will go deeper into the engine itself. We will examine what happens at the event horizon of a supermassive black hole, the place where physics as we understand it begins to collapse. We will explore the magnetic fields that thread the accretion disk, the jets of particles that may erupt from the poles, the relativistic effects that warp time and space in ways that Newton could not have imagined and Einstein could barely calculate. We will ask how this black hole grew so large so fast, and whether the answer tells us something troubling about the earliest era of cosmic history. And we will return to the question that haunts the edges of this discovery. What else is hiding in the data? What other monsters have we already photographed, already catalogued, already filed away under names that mean nothing because we did not understand what we were seeing? The archives are full of light. Some of that light has not yet been properly read. J0529-4351 waited 43 years for someone to notice. It burned with the fury of 500 trillion suns, and we called it a star. The universe does not label its monsters. It leaves them for us to find. Now we descend into the machinery. Picture the centre of J0529-4351. Not from a safe distance, not as a diagram in a textbook, but as a place you could theoretically approach. You cannot survive this approach, of course. Nothing made of atoms can survive it. but follow the thought experiment anyway, because the physics of what happens here is stranger than almost anything else in the universe, and understanding it requires imagining it as a real environment, a location with properties and behaviours that follow from the same equations that govern the motion of planets and the fall of apples on Earth. You begin your descent from far away. At first, the quasar is just a brilliant point of light, impossibly bright against the darkness. As you approach, that point resolves into a disk, a swirling platter of incandescent matter rotating around an invisible centre. The disk glows white-blue at its inner edge, transitioning through yellows and oranges to a deep red at its outer reaches, 7 light-years across. Think about what that means. If you were standing at the outer edge of this disk and shone a flashlight toward the centre, the beam would take 7 years to arrive. The disk is a structure so vast that light itself crawls across it, like a message sent by sailing ship. The material in this disk is not uniform. It is turbulent, chaotic, threaded with magnetic field lines that twist and tangle as the differential rotation of the disk drags them around. The inner regions orbit faster than the outer regions because orbital velocity depends on distance from the centre. This differential rotation shears the magnetic fields, amplifying them, creating loops and arcs of magnetic force that erupt from the disk surface like solar prominences on the sun, but scaled up by factors of billions. These magnetic structures are not decorative. They are part of the engine. They carry energy. They accelerate particles. They may be responsible for launching the relativistic jets that we will discuss later. As you approach closer, the temperature rises. The outer reaches of the disk are merely hot, perhaps tens of thousands of degrees, comparable to the surface of a hot star. But the inner regions, where matter spirals in toward the event horizon, reach temperatures measured in hundreds of millions of degrees. At these temperatures, atoms cannot hold together. The electrons are stripped away from their nuclei. What remains is plasma, a seething soup of protons and electrons and high-energy photons, all interacting in a continuous blaze of collisions and emissions. This is where the light comes from. The gravitational potential energy of infalling matter is converted into heat as friction and magnetic stresses slow the material's descent. The heat is radiated as light, across every wavelength from radio to gamma rays. The disk screams its presence to the cosmos in every colour of the electromagnetic spectrum. Closer still. Now you begin to feel the relativistic effects. Space and time behave differently here. The curvature of space-time, caused by the immense concentration of mass at the centre, stretches distances and dilates time. If you were watching from a safe distance, you would see the light from the inner disk redshifted, its wavelength stretched by the effort of climbing out of the gravitational well. Photons emitted as blue light at the inner edge arrive at your distant telescope as red or infrared, their energy diminished by the tax that gravity exacts on everything trying to escape. And if you were falling inward, if you were somehow surviving the radiation and the heat and the magnetic chaos, you would notice something strange about your own experience of time. Your clock would tick normally, from your perspective. But compared to clocks far away, your time would slow. Hours would pass for you while centuries passed for observers watching from Earth. And as you approach the event horizon, this effect would accelerate. Time would dilate toward infinity. From your perspective, you would continue falling. From the perspective of a distant observer, you would appear to slow, to redden, to freeze at the horizon, your image spreading and dimming until it faded below detection. You would never seem to cross. You would hover at the boundary forever, a ghost image trapped at the edge of the unknowable. This is the event horizon. The point of no return. It is not a surface, not a wall, not a barrier you can touch. It is a mathematical boundary, a sphere defined by the Schwarzschild radius, inside of which the escape velocity exceeds the speed of light. Nothing that crosses it can ever return. Light itself cannot climb out. Information cannot escape. Whatever falls in is gone, removed from the observable universe, added to the mass of the black hole but otherwise lost to us. For the black hole at the heart of J0529-4351, the event horizon is enormous. The Schwarzschild radius scales with mass. A black hole of 17 billion solar masses has an event horizon roughly 50 billion kilometers in diameter. That is about 350 times the distance from the Sun to Earth. You could fit the entire inner solar system, Mercury and Venus and Earth and Mars and the asteroid belt, inside this black hole with room to spare. The event horizon is not a pinprick. It is a region of space larger than many planetary systems, a zone of darkness embedded at the centre of that blazing disk like the pupil of some cosmic eye. And here is where the numbers become genuinely difficult to imagine. 1 solar mass of material per day, that is the feeding rate of this black hole. It sounds almost manageable when stated like that. 1 sun per day. But think about what that means in practical terms. The Sun is a middle-sized star. It contains more than 300,000 times the mass of Earth. Every day, J0529-4351 consumes that much matter. Every day, an amount of material equivalent to our entire star, the source of all warmth and light and life in our solar system, spirals past the event horizon and vanishes into the black hole's interior. The Earth itself weighs about 1/300,000th of the Sun. So the black hole consumes roughly 300,000 Earths per day, 12,000 Earths per hour, 200 Earths per minute, more than 3 Earths per second. Stop and feel the weight of that. Every second you have been listening to this narration, if you were somehow watching the event horizon of J0529-4351 in real time, you would have seen the equivalent of more than 3 Earths worth of matter disappear into the darkness. Not destroyed exactly. The matter still exists in some sense. Its mass contributes to the black hole's gravity, but it is gone from the universe as we can interact with it. It has passed beyond the horizon. It has fallen into a region from which no signal can return. 3 Earths per second consumed and silenced, their atoms crushed into whatever strange state matter assumes inside a black hole, a state that our physics cannot yet describe. This is why Christian Wolff called it the most violent place in the universe. Violence is not just about explosions or collisions, it is about transformation, about the permanent removal of matter from the realm of the accessible. J0529-4351 is a machine for taking reality and erasing it, piece by piece, at a rate that dwarfs any other process we have observed. The accretion disk is the fuel reservoir. 7 light-years across, it contains enough matter to sustain this feeding frenzy for eons. But even at this rate, the disk is not infinite. The material has to come from somewhere. It is drawn from the surrounding galaxy, from gas clouds and disrupted stars and smaller black holes that wander too close to the central engine. The quasar era, when objects like J0529-4351 shine at their brightest, occurs when there is abundant fuel, when the host galaxy is still assembling itself, when mergers and collisions and gravitational interactions are constantly stirring new material into the maw. We are seeing this object as it was 12 billion years ago. The universe at that time was less than 2 billion years old. It was an era of violent activity, of rapid star formation, of frequent galaxy mergers, of conditions that we do not see in the local universe today. The fuel supply was rich. The black holes that had formed in the earliest generations were growing rapidly, consuming their environments, shining like beacons across the young cosmos. Feustein 4351 is a snapshot of that era, a fossil record of the time when supermassive black holes were in their adolescence, feeding and growing at rates that seem impossible by the standards of the sedate, mature universe we inhabit. But here is the puzzle that has troubled astrophysicists for decades. How did these black holes get so large so fast? 17 billion solar masses is an extraordinary number. It takes time to accumulate that much material. Even at the prodigious rate of 1 solar mass per day, it would take 17 billion days to reach that mass. That is roughly 46 million years, which sounds long, but is actually a blink by cosmic standards. The problem is that black holes cannot sustain that feeding rate indefinitely. There are limits built into the physics. The primary limit is called the Eddington luminosity. It is named after the British astrophysicist Arthur Eddington, who in the 1920s calculated the maximum brightness that a star could achieve before radiation pressure would blow away any additional infalling material. The same limit applies to accreting black holes. As matter falls into the disk and heats up, it radiates light. That light exerts pressure on the surrounding gas. If the black hole tries to feed too fast, it produces so much light that the radiation pressure pushes back against the infalling material, creating an outward force that counteracts the inward pull of gravity. There is a maximum feeding rate that depends on the black hole's mass, and exceeding that rate causes the accretion to stall. J0529-4351 is feeding at or very near this Eddington limit. It is consuming matter almost as fast as physics allows. And yet, even at this maximum rate, building a black hole of 17 billion solar masses in the time available is difficult. The universe was less than 2 billion years old when we observed this quasar. Starting from a small seed black hole, perhaps the collapsed core of an early massive star weighing tens or hundreds of solar masses, how do you grow to 17 billion solar masses in less than 2 billion years? The math does not work cleanly. If you start with a 100 solar mass black hole and let it accrete at the Eddington limit continuously, doubling its mass roughly every 50 million years, you would need about 30 doubling times to reach 17 billion solar masses. 30 doublings times 50 million years is 1.5 billion years. That is barely possible in the time available, but only if the accretion is continuous, uninterrupted, sustained at the maximum rate for the entire period. Any pause, any interruption in the fuel supply, any deviation from optimal feeding, and the black hole falls behind. The real universe is not so cooperative. Fuel supplies fluctuate. Galaxy mergers are messy. Gas does not always flow efficiently into the central engine. The expectation from simulations and theoretical models is that black hole growth should be episodic, not continuous. There should be gaps, periods of relative quiescence between feeding frenzies. And yet here is J0529-4351. 17 billion solar masses in a universe less than 2 billion years old. How? There are several possible answers, and none of them is entirely satisfying. One possibility is that the seed black holes were much larger than we thought. Perhaps the first black holes did not form from stellar collapse at all. Perhaps they formed directly from the gravitational collapse of enormous gas clouds in the early universe, clouds that were too massive to fragment into stars and instead collapsed wholesale into black holes weighing tens of thousands or even hundreds of thousands of solar masses. These are called direct collapse black holes, and they would give early growth a significant head start. A seed of 100,000 solar masses needs far fewer doublings to reach 17 billion than a seed of 100 solar masses. Another possibility is that the Eddington limit can be exceeded under certain conditions. There is a process called super-Eddington accretion, where the geometry of the inflow allows material to fall in even as radiation is trying to push it out. If the accretion disk is thick rather than thin, if the radiation can escape along the poles while material falls in through the equator, then feeding rates above the classical Eddington limit become possible. Some models suggest that black holes in the early universe could accrete at 10 or even 100 times the Eddington rate under the right conditions. This would dramatically accelerate growth. A third possibility involves mergers. Black holes can grow not just by eating gas, but by eating other black holes. In the crowded, violent environment of the early universe, where galaxies were colliding frequently, the central black holes of merging galaxies would eventually spiral together and coalesce. A black hole of 1 billion solar masses merging with another black hole of comparable size would produce a 2 billion solar mass black hole in a single event, skipping over the slow process of gas accretion entirely. A few such mergers in the early history of J0529-4351's black hole could explain much of its mass. The truth is probably some combination of all three: heavy seeds, occasional super-Eddington episodes, mergers with smaller black holes along the way. But even with all these mechanisms invoked, the existence of objects like J0529-4351 pushes our models to their limits. It suggests that the early universe was even more extreme than we thought, that the conditions for rapid black hole growth were more common or more favourable than our simulations predict. It is a challenge to theory, a data point that forces refinement and reconsideration. And this is why discoveries like J0529-4351 matter beyond their record-breaking status. They are not just entries in a cosmic census. They are tests of our understanding. They probe the physics of the early universe, the mechanisms of black hole formation and growth, the relationship between galaxies and their central engines. When a black hole this massive appears this early, it tells us that something in our standard picture is either missing or wrong. Perhaps direct collapse black holes were more common than we thought. Perhaps super-Eddington accretion was more prevalent. Perhaps the earliest galaxies were denser, more gas-rich, more efficient at funneling material into their cores. Every hypothesis has implications that can be tested with further observations. The accretion disk itself holds clues. Its enormous size, 7 light-years across, suggests that the fuel supply is vast and well organised. The black hole is not scraping by on scraps. It is embedded in a reservoir of material large enough to sustain its growth for extended periods. The geometry of the disk, its thickness, its temperature profile, its magnetic structure, all of these encode information about the accretion process. Future observations, with better instruments and higher resolution, may be able to measure these properties in detail, distinguishing between models of thin disk and thick disk accretion, constraining the feeding rate more precisely, determining whether super-Eddington flow is occurring. And there are the jets. Many quasars produce relativistic jets, beams of particles accelerated to nearly the speed of light, shooting outward from the poles of the black hole perpendicular to the accretion disk. These jets are powered by magnetic fields anchored in the disk and twisted by the black hole's rotation. They can extend for hundreds of thousands of light-years, ploughing through the surrounding intergalactic medium, depositing energy and shaping the evolution of the host galaxy and its neighbours. Not all quasars show jets, and we do not yet know whether J0529-4351 is one of the jetted variety. If it is, those jets would be among the most powerful in the universe, given the energy available from the accretion process. They would be another window into the physics of the central engine. The rotation of the black hole matters here. In general relativity, a rotating black hole is described by a different solution to Einstein's equations than a non-rotating one. The rotating solution is called the Kerr metric, named after the New Zealand mathematician Roy Kerr, who discovered it in 1963. A Kerr black hole drags space-time around with it as it spins, an effect called frame dragging. This effect is strongest near the event horizon, where space-time itself rotates in the same direction as the black hole, carrying everything along with it regardless of the object's own motion. Frame dragging has been measured in our solar system, using satellites in orbit around Earth, where the effect is tiny but detectable. Near a supermassive black hole spinning at significant fraction of its maximum rate, frame dragging is intense. It shapes the innermost regions of the accretion disk. It influences where material can orbit stably and where it must plunge inward. It affects the efficiency with which gravitational energy is converted to radiation. A maximally rotating black hole can convert up to 42% of the rest mass energy of infalling material into radiation. A non-rotating black hole can convert only about 6%. The difference is enormous. A spinning black hole is a more efficient engine. J0529-4351, shining at 500 trillion solar luminosities, is almost certainly spinning rapidly. If it were not, the mass accretion rate required to produce that luminosity would exceed even the most generous estimates. The spin is part of what makes it so bright. The spin is part of what makes it so dangerous. We have travelled now from the outer reaches of the accretion disk through the turbulent middle regions down toward the event horizon, and we have glimpsed something of the physics that governs this engine. But there is more. There is the question of what lies beyond the horizon, inside the black hole, in the realm where our physics breaks down and our mathematics produces infinities and our understanding fails. This is the singularity, or rather, this is what classical general relativity predicts lies at the centre, a point of infinite density, infinite curvature, where all the infalling matter and energy are crushed into zero volume. The singularity is a prediction of the theory, but it is also a confession of ignorance. When a physical theory predicts infinity, it usually means that the theory has exceeded its domain of validity. Infinities are not physical. They are signals that something is missing, that we need a deeper theory to describe what actually happens. The deeper theory, presumably, is one that unifies general relativity with quantum mechanics. We do not yet have such a theory. We have candidates, string theory and loop quantum gravity and others, but none of them has been tested, none of them has produced predictions that can be verified observationally. The interior of a black hole is one of the places where this missing physics matters most. What really happens at the centre? Is there a singularity or not? Is space-time itself quantized, preventing the infinite compression that classical theory predicts? Does information about the infalling matter survive in some form, encoded in quantum states that we do not yet understand? These are open questions. They are among the deepest questions in physics, And black holes like the one powering J0529-4351 are the laboratories where the answers hide, behind a horizon that we cannot cross, in a region that we cannot probe with any signal, holding secrets that may take centuries or millennia to unlock. For now, we study what we can: the light that escapes, the spectra that encode the composition and motion of the gas, the luminosity that tells us the feeding rate, the redshift that tells us the distance, the variability that tells us about the structure and stability of the disk. These are our only handles on the machine. The interior is closed to us. The singularity, if it exists, is unknowable. But the exterior is enough to inspire awe and unease in equal measure. 17 billion solar masses, one sun consumed per day, 500 trillion solar luminosities, 7 light-years of accretion disk, 12 billion light-years of separation, 43 years of hiding in plain sight. This is what was waiting in the archives. This is what we missed. But let us not leave the singularity behind too quickly. Let us linger at the edge of what we know, at the boundary where physics becomes poetry and mathematics becomes metaphor. Because this boundary is not merely an intellectual curiosity. It is a mirror. It reflects back to us the limits of our own understanding, the shape of our ignorance, the contours of the questions we have not yet learned how to ask. The singularity, as general relativity describes it, is not a place in the ordinary sense. It is not a point you could visit, a location you could map, a destination you could approach and then retreat from. It is something stranger. It is a point in time. For an observer falling into a non-rotating black hole, the singularity lies in their future, the same way that tomorrow lies in yours. You cannot avoid it any more than you can avoid next Tuesday. Once you have crossed the event horizon, every possible path through space-time leads to the singularity. There is no sideways. There is no retreat. There is only forward, and forward ends. This is difficult to feel. Our intuitions about space and time are shaped by the weak gravitational fields we inhabit, where space is space and time is time, and the two are clearly distinguished. Inside a black hole, that distinction dissolves. The radial direction, the direction that pointed away from the centre when you were outside, becomes time-like. Moving outward becomes as impossible as moving backward in time. The geometry of space-time itself has rotated, mixing space and time into something our minds were not built to comprehend. And at the singularity, if classical general relativity is correct, even that strange geometry fails. Curvature becomes infinite. Tidal forces become infinite. The equations themselves break down, producing not predictions but paradoxes. A falling observer would be stretched along their direction of fall and compressed along the perpendicular directions, a process physicists call spaghettification. The name is grimly whimsical. The reality is annihilation. Long before reaching the singularity, any physical structure would be torn apart. Then the atoms would be torn apart. Then the particles themselves would be subjected to forces that no known physics can describe. But J0529-4351 is not an ordinary black hole. It is almost certainly rotating, spinning at a significant fraction of its maximum possible rate. And rotating black holes have a different interior structure. The singularity is not a point, but a ring. The geometry includes not one horizon, but two, an outer event horizon and an inner Cauchy horizon. Between them lies a region where space-time behaves even more strangely, where closed time-like curves may exist, where cause and effect become entangled in ways that seem to permit paradoxes. Stop and feel the strangeness of that. Inside the black hole at the heart of J0529-4351, if classical general relativity is correct, there may be regions where the future connects back to the past, where an observer, in principle, could meet their earlier self, where the linear flow of time that governs our entire experience becomes a loop. No one knows if these features survive in a complete theory of quantum gravity. The Cauchy horizon is unstable in classical general relativity. In falling, radiation gets blue-shifted to infinite energy as it approaches, suggesting that the interior structure predicted by the Kerr solution may be destroyed by the very act of forming. What lies beyond may be something entirely different, something we have not yet imagined, something that requires concepts we have not yet invented. This is the machine hiding at the centre of J0529-4351, not merely a gravitational well of staggering depth, but a laboratory for the most extreme physics in the universe, a place where general relativity and quantum mechanics collide, a place where the fabric of space-time is twisted into configurations that challenge our most basic assumptions about reality, a place that has been shining its light toward us for over 12 billion years, patient as stone, waiting for someone to look up and notice. Now let us step back from the mathematics and remember that we are talking about a real object, a thing that exists, a structure of matter and energy and curved space-time that is out there right now, at this very moment, 12 billion light-years away, consuming a star's worth of material every day, shining with the light of 500 trillion suns. When we point our telescopes at that patch of sky, in the constellation Pictor, we are looking at light that left its source before the Earth existed, before the Sun existed, before the Milky Way had taken its current form. The photons entering our instruments tonight were emitted when the universe was less than 2 billion years old, when the first galaxies were still assembling from primordial gas, when the cosmic web of filaments and voids was still being woven. In some sense, the quasar we see is a ghost. The light is ancient. The object that emitted it may no longer exist in its current form. 12 billion years is an enormous span of time. Quasars are not eternal. They are phases in the lives of galaxies, periods of intense activity when the central black hole has abundant fuel and feeds voraciously. Most quasars eventually fade as their fuel supply dwindles. The black hole remains, but the accretion disk thins, the jets weaken, the luminosity drops. What was once the most violent place in the universe becomes a quiet darkness, a gravitational anchor around which stars orbit in eternal silence. What does the centre of the galaxy that hosted J0529-4351 look like today? We cannot know. No signal can travel faster than light. The present state of that distant system is hidden from us, veiled by the simple fact that information takes time to propagate across the cosmos. We see the past. We can only see the past. Every observation in astronomy is archaeology. But this temporal separation does not diminish the significance of what we are seeing. Quite the opposite. It amplifies it. Because what we are observing is not merely a powerful object, it is a window into a particular epoch of cosmic history. A time when supermassive black holes were growing with terrifying speed. A time when the universe was denser, hotter, more turbulent. A time when the foundations of the present were being laid. The black hole at the heart of J0529-4351 weighs 17 billion solar masses. That is an almost inconceivable amount of material compressed into a region of space smaller than our solar system. To accumulate that much mass takes time. It takes enormous quantities of infalling gas. It takes specific conditions that we are still working to understand. Here is the puzzle that haunts astronomers who study the early universe. Supermassive black holes like this one should not exist so soon. If they grew from stellar remnants, the small black holes left behind when massive stars explode, they should not have had time to reach 17 billion solar masses by the time the universe was less than 2 billion years old. The arithmetic does not work. Let me unpack this slowly. When a massive star exhausts its nuclear fuel and collapses, it can form a black hole. These stellar mass black holes typically weigh between a few and a few dozen solar masses. They are small by the standards of supermassive black holes. To grow from a few dozen solar masses to 17 billion solar masses requires consuming an enormous amount of material, and there is a limit to how fast a black hole can consume. This limit is called the Eddington limit. It arises from the balance between gravity pulling material inward and radiation pushing material outward. When material falls into a black hole, it heats up and radiates intensely. If the accretion rate is too high, the radiation pressure becomes so strong that it blows the infalling material away, preventing further feeding. The Eddington limit is the maximum luminosity, and therefore the maximum accretion rate, at which a black hole can feed without its own radiation stopping the process. At the Eddington limit, a black hole doubles its mass in a characteristic time called the salpeter time, roughly 45 million years for typical assumptions. Starting from a stellar mass black hole and doubling every 45 million years, how long would it take to reach 17 billion solar masses? The answer is troubling. It would take longer than the age of the universe was when we see J0529-4351. The numbers do not add up. Even continuous Eddington-limited accretion from the very beginning of time would not produce a 17 billion solar mass black hole by the time the universe was 1.4 billion years old. This is one of the deep puzzles of early universe cosmology. We call them the seeds problem. Where did the seeds of supermassive black holes come from? How did they grow so large so fast? Several solutions have been proposed. Perhaps the initial seeds were not stellar mass black holes, but something heavier. Perhaps the first generation of stars, the population 3 stars that formed from pure hydrogen and helium, were much more massive than stars today, collapsing directly into black holes of hundreds or even thousands of solar masses. Perhaps in some dense environments, massive gas clouds collapse directly into black holes without ever forming stars, creating seeds of tens of thousands of solar masses. Perhaps some black holes manage to exceed the Eddington limit for sustained periods, feeding in a mode called super-Eddington accretion, where the geometry of the infale allows more material to reach the horizon than simple radiation pressure arguments would suggest. J0529-4351 may be feeding in exactly this super-Eddington mode. Its luminosity is so extreme, its mass accretion rate so high, that it may be operating at or beyond the classical limit. The physics of such accretion is not fully understood. When radiation pressure becomes overwhelming, the geometry of the accretion disk may change. Material may fall in along the poles while radiation escapes along the equator, or vice versa. The disk may become geometrically thick, puffing up under its own radiation pressure, trapping some of the light and allowing the accretion rate to exceed what simple models predict. Think of it this way. The Eddington limit is derived by assuming that radiation pushes outward in all directions equally. But if the accretion flow is not spherically symmetric, if there are directions where radiation can escape more easily, and directions where material can fall in more easily, then the effective limit can be higher. The black hole can eat faster than the simple calculation suggests, and if it can eat faster, it can grow faster, and if it can grow faster, perhaps the seeds problem has a solution after all. J0529-4351, then, is not merely a spectacular object. It is evidence. It is a data point in our attempt to understand how the universe built its first giant black holes. It is telling us something about the conditions in the early universe, about the physics of extreme accretion, about the processes that shape the galaxies we inhabit today. But here is another way to think about it. Here is another frame. 17 billion solar masses. 1 sun per day, 500 trillion solar luminosities. These are the numbers we keep returning to, the numbers that define this object, the numbers that make it the most luminous thing ever found. But what do they mean in terms we can feel? Let us try once more to give you a feel for the violence. The accretion disk is 7 light-years across. That is, roughly speaking, the distance from the Sun to its nearest neighbouring star multiplied by twice. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. The accretion disk of J0529-4351 would reach from the Sun past Proxima Centauri and continue another 2.7 light-years beyond. It would swallow the nearest star. It would swallow the next nearest. It would fill a volume of space that contains, in our neighbourhood, exactly 2 other stars, and this entire disk is glowing, radiating. Every square metre of its surface is emitting photons at temperatures that exceed the surfaces of most stars. The inner regions, near the event horizon, are so hot that they emit X-rays and gamma rays. The outer regions, cooler but still incandescent, emit ultraviolet and visible light. The total output is equivalent to 500 trillion suns burning simultaneously. Try to picture that. 500 trillion. That is 500,000, 500,000 billion. If you started counting at 1 number per second, you would not reach 500 trillion in your lifetime. You would not reach it in the lifetime of human civilization. You would need about 15 million years of continuous counting. That is the number of suns this object outshines. Every second. Continuously. For as long as it has fuel. And it does have fuel. The accretion disk is being replenished by material from the host galaxy. Gas clouds fall inward, drawn by the black hole's immense gravity. Stars that wander too close are torn apart by tidal forces, their material added to the disk. The merger history of the galaxy itself may have channeled vast quantities of gas toward the centre. The black hole is embedded in a reservoir of potential fuel that could sustain its feeding for millions or even billions of years. This is what the early universe was like. This is what it meant to live in the first 2 billion years. Giant black holes growing without restraint. Accretion disks the size of stellar neighbourhoods. luminosities that would sterilize any planet within millions of light years. Radiation so intense that it ionized the surrounding intergalactic medium, clearing bubbles of transparency in the primordial fog. We call this the epoch of reionization. In the first several 100 million years after the Big Bang, the universe was filled with neutral hydrogen, a fog that was opaque to most forms of light. Then the first stars ignited, then the first galaxies assembled, then the first quasars turned on, and the radiation from these sources began to ionize the hydrogen, stripping electrons from atoms, converting the fog into a plasma that was transparent to light. J0529-4351 was part of this process. Its radiation, shining at 500 trillion solar luminosities, carved a bubble of ionized gas around it. It contributed to the transformation of the early universe from opacity to transparency. It was, in a sense, one of the lights that ended the cosmic dark ages. And now that light has reached us, 12 billion years after it was emitted, 43 years after it was first recorded on a photographic plate, 1 year after its true nature was finally recognized. Think about that timing. The light travels for 12 billion years. It enters the atmosphere, it falls on a detector, it is recorded, it is catalogued, it is assigned a designation, a star, and then it waits. It waits in the archive while astronomers study other things. It waits while telescopes improve, while software improves, while machine learning algorithms are developed to scan the vast databases that surveys generate. It waits while thousands of other quasars are discovered, catalogued, studied, published. It waits while the universe itself ages by another 43 years, while the Earth completes 43 orbits around the Sun, while generations of astronomers are born and trained and retire and die. And then someone looks again. Someone trains a new algorithm, someone checks the old data with new tools, and the star becomes a quasar. The ordinary becomes extraordinary. The overlooked becomes the record holder. This is how discovery works. Not always as a flash of insight, not always as a moment of revelation. Sometimes as a slow correction of accumulated errors. Sometimes as the patient re-examination of data that was always there, always available, always waiting for someone to see it clearly. The archives are full of such objects. We know this now with a certainty that borders on discomfort. The surveys we have conducted, the catalogues we have built, the databases we have assembled, they contain discoveries we have not yet made. Objects misidentified, signals misinterpreted, patterns unrecognized. The most luminous object in the universe hid for 43 years. What else is hiding? This question is not merely rhetorical. It is a research program. Astronomers are now revisiting old surveys with new techniques, searching for the next J0529-4351, searching for the objects that automated systems flagged incorrectly, searching for the needles in the haystack that were mistaken for hay. Machine learning is central to this effort. The same neural networks that failed to identify J0529-4351 as a quasar are being retrained, refined, improved. They are learning from their mistakes. They are being fed examples of the edge cases, the objects that lie in the ambiguous zones between categories, the sources that could be stars or could be quasars or could be something else entirely. But machine learning has limits. Neural networks learn from examples. They generalize from the data they have seen. If the training set does not contain examples of a particular type of object, the network will not recognize that type. It will assign the unknown object to the nearest known category. It will make the same mistake that was made with J0529-4351. It will see a quasar and call it a star. The solution is not merely more data or better algorithms. The solution requires human intuition, human skepticism, human willingness to question the outputs of automated systems. The discovery of J0529-4351 was made not by a machine but by humans who looked at the machine's results and said, "Wait, this doesn't look right. Let us check again." This is the partnership that modern astronomy requires. Machines to process the overwhelming volume of data. Humans to guide the machines, to train them, to correct them, to ask the questions that machines do not know how to ask. Neither alone is sufficient. Together, they are capable of discoveries that neither could make independently. And there will be more discoveries. There will be more J0529-4351s hiding in the archives. There will be objects even more luminous, even more massive, even more distant. There will be surprises that we cannot anticipate because our categories are still incomplete, our understanding still fragmentary, our instruments still limited. The universe is larger than our imagination. It contains phenomena that we have not yet conceived. It operates according to principles that we have not yet discovered. Every time we think we have mapped its extremes, it shows us something more extreme. Every time we think we have reached the limits, it reveals that the limits are farther than we thought. J0529-4351 is the current record holder, the most luminous object ever discovered, the fastest growing black hole ever found, the largest accretion disk ever measured, but it will not hold these records forever. Somewhere in the archives, or somewhere in the data that will be collected tomorrow, is the next record holder, the next extreme, the next impossible object that will force us to revise our models and expand our understanding. This is the nature of the enterprise. This is what it means to study the universe. Not to reach a final answer, but to ask an endless series of questions. Not to complete a catalogue, but to realise that every catalogue is incomplete. Not to solve the mystery, but to discover that every solution reveals deeper mysteries. The black hole at the heart of J0529-4351 weighs 17 billion solar masses. It has been feeding for billions of years. It will continue to feed for billions more, until its fuel supply dwindles and the accretion disk fades and the quasar falls silent. What will remain is the black hole itself, dark and patient, carrying within its horizon all the matter and energy it has ever consumed, holding secrets that the universe may never surrender. And we will still be here, or our descendants will, peering upward with whatever instruments we have built, asking the same questions we ask now. What is out there? What have we missed? What is hidden in plain sight? The question takes on a different weight when you realise that J0529-4351 was not the first quasar to be misidentified. It was not even the 100th. The history of quasar discovery is, in many ways, a history of mistakes. A history of objects that should have been found decades earlier but were not. A history of data that sat waiting in archives, patient and indifferent, while astronomers looked right past it. Consider the very first quasar ever identified. In 1963, astronomer Martin Schmidt was studying a radio source catalogued as 3C273. Radio astronomers had been detecting powerful emissions from this point in the sky for years. They knew something was there, but when optical astronomers pointed their telescopes at the same location, all they saw was what appeared to be a faint blue star. Just another star among billions. Not interesting. Not worth a closer look. Schmidt decided to take a spectrum anyway. He spread the light from this apparent star through a prism and examined the resulting rainbow of colours for the telltale absorption and emission lines that reveal a star's composition and temperature. What he saw made no sense. The lines were there, but they were in the wrong places. They were shifted toward the red end of the spectrum by an amount that seemed impossible for a star in our own galaxy. He spent weeks trying to make the data fit. He tried different calibrations. He tried different assumptions. Nothing worked. The lines remained stubbornly in the wrong places, and then, in a moment that changed astronomy forever, he realized the truth. The lines were not in the wrong places at all. They were exactly where they should be for hydrogen, but hydrogen moving away from us at nearly 50,000 kilometers per second. This was not a star. This was something vastly more distant, vastly more luminous, vastly more energetic than any star could be. The redshift told him that 3C273 was not a few hundred light-years away, as a star in our galaxy would be. It was 2 billion light-years away. At that distance, to appear as bright as it did, it had to be shining with the light of 100 ordinary galaxies. A new category was born: quasi-stellar radio sources, quasars, objects that looked like stars but were not stars, objects that defied every expectation, objects that forced astronomers to imagine engines of luminosity far beyond anything they had previously conceived. And here is the uncomfortable truth that rarely gets mentioned in the triumphant retelling of Schmidt's discovery. 3C273 had been photographed repeatedly for decades before 1963. It appeared on photographic plates dating back to the late 19th century. Every time astronomers looked at it, they saw what they expected to see: a blue star, not particularly bright, not particularly interesting. One mote of light among millions of motes of light. They had the data. They simply did not know what they were looking at. The universe had been showing them quasars for 70 years before anyone recognized one. This pattern repeats throughout the history of astronomy. We see what we expect to see. We sort observations into familiar categories. We file the anomalies away as errors or curiosities or things to investigate later, if we ever get around to it. And sometimes, decades later, someone pulls out those old observations and realizes that the anomaly was not an error at all. It was a discovery waiting to be made. Pulsars were discovered in 1967 by Jocelyn Bell, a graduate student at Cambridge. She noticed a strange signal in the radio data, a regular pulse, ticking once every 1.337 seconds, with such precision that she and her supervisor briefly considered whether it might be an artificial signal from an alien civilization. They gave it the half-joking designation LGM-1, for Little Green Men. Further investigation revealed that the signal was coming from a rapidly spinning neutron star, a stellar corpse so dense that a teaspoon of its material would weigh 1 billion tons. But here is the part that usually gets left out. That same pulsing signal had been recorded years earlier by other radio telescopes. It was sitting in archived data, flagged as interference, dismissed as equipment malfunction, filed away, and forgotten. The universe had been sending the signal for years. We just were not listening. The same pattern held for gamma-ray bursts, the most energetic explosions in the universe. They were first detected in 1967 by American military satellites designed to watch for secret Soviet nuclear tests. The satellites kept detecting brief flashes of gamma rays coming from random directions in space. For years, the military classified the data, uncertain what to make of it. When the information was finally declassified and shared with astronomers, they had no idea what they were looking at either. It took decades to determine that these flashes were coming from distant galaxies, from collapsing stars and merging neutron stars billions of light years away. The detections had been recorded, the data existed, the mystery persisted because no one knew what questions to ask. And now we come back to J0529-4351, sitting in archives since 1980, misidentified as a star, patient and indifferent to human confusion. It was photographed by the S.O. Schmidt Southern Sky Survey when the Voyager probes were still travelling through the outer solar system. The data has existed for 44 years. Generations of astronomers have looked at that data. Automated systems have processed it. Machine learning algorithms have analysed it. And still, it was not until 2023 that anyone realised what they were looking at. Stop and feel the weight of that. 44 years of scientific progress. 44 years of increasingly sophisticated instruments and increasingly powerful computers and increasingly clever algorithms. And the most luminous object in the known universe was hiding in plain sight the entire time. This is not a failure of science. This is science working exactly as it always does. We build tools to see the universe. The tools show us things we're not prepared to understand. We misinterpret what we see. We make mistakes. We file anomalies away as errors. And then, slowly, painfully, one correction at a time, we learn to see what was always there. The question is not why J0529-4351 was missed for so long. The question is what else we are missing right now. The archives of modern astronomy contain petabytes of data. Every major survey generates more information than any team of humans could examine in a lifetime. The Sloan Digital Sky Survey has catalogued hundreds of millions of objects. The Dark Energy Survey has mapped 300 million galaxies. The Vera Rubin Observatory will add billions more. ESA's Gaia satellite has measured the positions and motions of nearly 2 billion stars. The upcoming Euclid mission will survey 15 billion sources. Within this ocean of data, how many J0529-4351s are hiding? How many record-breaking objects are sitting in databases, misclassified, waiting for someone to notice that something does not add up? The answer is certainly not zero. The answer might be hundreds. It might be thousands. It might include categories of objects we have not yet imagined. Phenomena so strange that our current algorithms cannot even flag them as unusual, because they do not fit into any of our existing templates. This is the frontier where modern astronomy operates. Not at the edge of what our telescopes can see, but at the edge of what our minds can comprehend. The data is there. The photons have already been collected. The challenge is no longer gathering light. The challenge is understanding what the light is telling us. consider what it took to finally identify J0529-4351. The first clue came from a careful examination of the Gaia data. The satellite had flagged the object as a star, but it had also recorded how the object's brightness varied over time. Most stars have stable brightnesses, or they vary in predictable patterns, oscillations caused by surface pulsations or eclipses from orbiting companions. J0529-4351 did not vary like a star. Its brightness fluctuated in ways that were subtle, but wrong. Not the gentle oscillations of a pulsating giant. Not the periodic dips of an eclipsing binary. Something else. This was the first thread that Christopher Onken and Christian Wolff pulled on. The variability pattern looked more like what you would expect from an active galactic nucleus, a quasar or one of its cousins. The luminosity fluctuation suggested a dynamic system, something with an accretion disk where magnetic turbulence and gravitational instabilities caused the brightness to wander unpredictably over weeks and months. But this observation alone was not enough. Lots of objects show irregular variability. To confirm that they were looking at a quasar, the researchers needed a spectrum. They needed to see whether the light carried the telltale fingerprints of gas moving at relativistic velocities, gas superheated to millions of degrees, gas falling into a gravitational well so deep that it glows brighter than entire galaxies. The spectrum they obtained from the ANU 2.3-metre telescope settled the question. There, spread across the detector, were the broad emission lines of a quasar: hydrogen, carbon, magnesium. Each line smeared across a wide range of wavelengths, Doppler shifted by the frantic motions of gas orbiting close to the event horizon. And beneath those lines, unmistakable, was the signature of an accretion disk. The thermal continuum of superheated matter stretched across 7 light-years of space. The redshift told them the distance, more than 12 billion light-years. They were looking at an object that existed when the universe was barely 1 billion years old, an infant cosmos still learning to assemble its first structures. And the brightness told them the rest. At that distance, to appear as luminous as it did in their data, the object had to be shining with an intensity that broke every record in the books. 500 trillion solar luminosities, a beacon so bright that if you moved it to where the nearest star sits, just 4 light-years from Earth, it would outshine the full moon in our sky, from 4 light-years away. The discovery was made not by finding something new, but by looking again at something old. The data had been there all along. The photons had been collected decades ago. What was missing was the insight, the skepticism, the willingness to question the classifications that machines had assigned. This brings us to a deeper truth about how discoveries happen. The romantic image is of the lone genius peering through a telescope and suddenly glimpsing something no one has ever seen. The reality is messier. Discoveries emerge from a tangle of old data and new methods, of automated systems and human intuition, of mistakes recognized and corrections made. They emerge from the uncomfortable moment when an astronomer looks at a result and says, "This does not make sense." J0529-4351 did not make sense as a star. Its variability was wrong, its colours were slightly wrong, its position relative to the galactic plane was suspicious. Stars bright enough to be catalogued by sky surveys should be concentrated along the Milky Way's disk, but this object sat in an area of sky where foreground stars are relatively sparse. Each of these discrepancies was subtle. Each could be explained away individually, but together they formed a pattern that demanded closer inspection. The lesson here is not that machines are unreliable. Machines processed the data with perfect fidelity. They applied the algorithms they were given exactly as designed. The lesson is that the algorithms themselves embody assumptions about what exists in the universe. Those assumptions are necessarily incomplete. When the universe contains objects that fall outside the assumptions, the algorithms will fail. This is not a flaw that can be fixed by building better algorithms. Every algorithm is built on a model of reality, and every model is incomplete. The gap between model and reality is where discoveries hide. Think about what we're asking automated classification systems to do. We feed them millions of examples of known objects, stars with various temperatures and compositions, galaxies at various distances and orientations, quasars with various luminosities and redshifts. The system learns patterns. It learns that stars have certain colours, certain variabilities, certain spectral shapes. It learns that quasars have different patterns, and then we point it at the sky and ask it to sort billions of new objects into these categories. The system does what it was trained to do. It looks for similarity. It asks, which of the patterns I have learned does this new object most resemble? And if the new object does not quite fit any pattern perfectly, the system does what any pattern matcher must do. It picks the closest match and assigns a probability. For J0529-4351, the closest match was a star. The object was bright, very bright. Stars can be bright. Quasars are usually faint, distant smudges. This object looked like a point of light, just like a star. The algorithm made a reasonable judgment based on the patterns it had learned. It was wrong, but it was not stupid. It was doing exactly what we designed it to do. The problem was us. We had not anticipated that a quasar could be so luminous that it would appear star-like in our surveys. We had not trained the system on examples of this extreme. We had built our categories around the objects we knew, and we had assumed that the objects we knew were representative of the objects that exist. They were not. This is always the danger of inductive reasoning. You examine 1,000 swans and find that they are all white. You conclude that all swans are white. And then you sail to Australia and discover black swans. Black swans are everywhere in astronomy. Objects that break the rules. Objects that fall outside the distributions. Objects that force us to expand our categories because the old categories were too narrow. Neutron stars with magnetic fields a quadrillion times stronger than Earth's, magnetars, were black swans when first discovered. Fast radio bursts, mysterious millisecond flashes of radio waves coming from distant galaxies, were black swans. Objects in the outer solar system on orbits that seemed to require an unseen ninth planet were black swans. Each of these discoveries required someone to look at data that did not fit and say, this is not an error, this is something new. J0529-4351 is a black swan in the most literal sense, an object so extreme that our classification systems did not have a category for it, an object that sat in archives for 4 decades, wearing a disguise that our algorithms could not see through, an object that required human eyes and human skepticism to be recognized for what it truly is, and it will not be the last. The surveys coming online in the next decade will produce more data than all previous astronomical observations combined. The Vera Rubin Observatory will photograph the entire southern sky every 3 nights, cataloguing transient events and moving objects and variable sources with unprecedented completeness. The square-kilometre array, when complete, will be the most sensitive radio telescope ever built, capable of detecting signals that current instruments cannot even register. Space telescopes like Euclid and the Nancy Grace Roman Space Telescope will map the cosmos in wavelengths that ground-based observatories cannot access. All of this data will flow into archives. All of it will be processed by automated systems. All of it will be classified by machine learning algorithms that embody our current understanding of what exists in the universe. And hidden within that flood of information will be black swans, objects that do not fit, objects that the algorithms will miscategorize, objects that will wait, patient and indifferent, until someone notices that something is not quite right. The history of J0529-4351 is, in one sense, a cautionary tale, a reminder that our classification systems are imperfect, that our assumptions limit what we can see, that the universe is stranger and more extreme than our models predict. But it is also a hopeful tale, a reminder that discoveries are still possible, that even in an age of automation and big data, human insight matters, that the most luminous object in the universe can hide for 40 years and still eventually be found. What else is hiding? We do not know. That is the honest answer. We do not know how many J0529-4351s remain in the archives. We do not know what categories of objects our algorithms are blind to. We do not know what assumptions we have made that are narrower than the universe's actual variety. But we know that the discoveries are there, waiting. We know that somewhere in the petabytes of archived observations, there are anomalies that will become landmarks. There are outliers that will become new categories. There are mistakes waiting to be corrected and surprises waiting to be recognized. The universe is not yet fully catalogued. The map is not yet complete. And every time we think we have reached the edge of what exists, we find that the edge is farther than we thought. 17 billion solar masses, 500 trillion solar luminosities, 7 light-years across, a black hole feeding for 12 billion years. These numbers mark the current limits of what we have found. They do not mark the limits of what exists. The next record holder is out there. It may be in an archive we have already collected. It may require a telescope that has not yet been built. It may challenge our classification systems in ways we cannot predict. But it is out there, waiting to be found, patient and indifferent to human curiosity. The same sun that rose on the morning of J0529-4351's discovery will rise on the morning of the next discovery. The astronomers who make that discovery will do what astronomers have always done. They will look at data that does not fit. They will pull on threads that others have overlooked. They will say the words that precede every great discovery in the history of science. Wait, this doesn't look right. Let us check again. The checking never ends. That is perhaps the strangest truth about the scientific enterprise. We build instruments of staggering precision. We develop algorithms of extraordinary sophistication. We accumulate data in quantities that would have seemed magical to previous generations, and still we find ourselves checking, looking again, pulling threads. The universe does not present itself to us in organized packets of knowledge. It presents itself as light, as signals, as traces in detectors, and we must do the interpretive work of understanding what those traces mean. Consider what it means to measure something 17 billion light-years away. The photons that reach our telescopes began their journey when the universe was barely 1 billion years old. They have travelled through expanding space, their wavelength stretching as the cosmos itself stretched, their original colours shifting toward the red end of the spectrum in proportion to the distance they have crossed. By the time they reach Earth, they carry information about a place and a time so remote that the word distant feels inadequate. They carry whispers from an epoch when galaxies were still assembling themselves, when the first supermassive black holes were still growing toward the monsters they would become, when the cosmic web was still a scaffolding under construction. And what do we do with those photons? We collect them. One by one, over hours of integration time, we gather ancient light onto the sensors of our telescopes. Each photon that arrives is a survivor. Most of the light emitted by J0529-4351 will never reach any telescope. It radiates outward in all directions, spreading through expanding space, growing fainter with distance according to the inverse square law that governs all radiation. The fraction that happens to be aimed at the precise location where Earth will be 12 billion years later is vanishingly small. And yet even that vanishing fraction adds up to something measurable, because J0529-4351 is so extraordinarily luminous that its faint whisper across cosmic time is still bright enough to register. This is the paradox that fooled our algorithms. The object was bright. Bright objects in the sky are usually nearby. Stars are bright because they are close. Distant objects are faint because light spreads thin across space. An object that appears bright and turns out to be at cosmological distance must be outputting energy at a rate that beggars imagination. The automated systems did the sensible thing. They applied the prior probability. Bright objects are usually stars. This bright object is probably a star. The classification stuck. But probabilities are not certainties, and the universe is not obligated to follow our statistical expectations. Every prior we construct is based on what we have seen before, and what we have seen before is necessarily limited by the instruments we have built and the time we have spent looking. The first telescope was pointed at the sky barely 4 centuries ago. The first photographic plate of a celestial object was exposed less than 2 centuries ago. The first CCD detector was installed on a telescope within living memory. We have been systematically surveying the sky for the blink of an eye, cosmologically speaking. Our priors are constructed from a sample that is neither complete nor representative. They are educated guesses, nothing more. And educated guesses can be wrong. The correction of those guesses is the substance of scientific progress. Every paradigm shift, every reconceptualization of what the universe contains, begins with an observation that does not fit. Pulsars were discovered because a graduate student named Jocelyn Bell noticed a bit of scruff on a chart recorder printout that her supervisor had dismissed as interference. The cosmic microwave background was discovered because 2 engineers at Bell Labs could not explain the persistent hiss in their antenna and were meticulous enough to rule out every terrestrial source, including pigeon droppings. Dark energy was discovered because two teams measuring distant supernovae found that the universe was accelerating when every theoretical expectation said it should be decelerating. In each case, the discovery began with an anomaly, a piece of data that refused to be explained by existing models. In each case, the discovery required someone to take the anomaly seriously, to resist the temptation to dismiss it as error or noise or equipment malfunction. J0529-4351 is part of this tradition. It sat in the archives, not because anyone made a mistake in the ordinary sense, but because the classification system was working as designed. It was finding patterns, applying priors, sorting objects into categories based on the best available evidence. The system was not broken. It was limited, and the limitation was exposed only when human observers decided to look more carefully at objects that sat near the boundaries of the classification system's confidence. This is why the discovery matters beyond its record-setting numbers. It matters because it illuminates the process by which we come to know the universe. We build systems of extraordinary sophistication, and then we build systems to check those systems, and then we use human judgment to check the systems that check the systems. The chain of verification extends backward indefinitely, because at every level there are assumptions that might be wrong, priors that might be too narrow, categories that might not capture the full range of what exists. Let me take you now to the physical reality behind the numbers. We have spoken of 17 billion solar masses, of 500 trillion solar luminosities, of an accretion disk 7 light-years across. These are the measurements. But what do they correspond to in the actual fabric of space and time? Picture first the black hole itself. It does not have a surface in any conventional sense. There is no solid boundary, no membrane, no edge you could touch. Instead, there is a mathematical surface called the event horizon, a boundary beyond which escape becomes impossible. For a non-rotating black hole of 17 billion solar masses, the event horizon would have a radius of roughly 50 billion kilometres. That is not a typo. 50 billion kilometres. The orbit of Pluto around our Sun, at its farthest point, is about 7.5 billion kilometres from the Sun. The event horizon of this black hole would extend more than 6 times farther than Pluto's orbit. You could fit our entire solar system inside the event horizon multiple times over, with room to spare. But J0529-4351's black hole is almost certainly rotating. We know from observations of other quasars that the black holes at their centres are typically spinning, and spinning fast. Rotation changes the geometry of space-time around a black hole, dragging the fabric of the cosmos along with it, in a phenomenon called frame dragging. The event horizon of a rotating black hole is smaller than that of a non-rotating black hole of the same mass, and the region of extreme space-time distortion extends farther in certain directions. The precise spin of J0529-4351's black hole is not yet known. Measuring black hole spin requires detailed spectroscopic observations of the innermost regions of the accretion disk, observations that are challenging even for nearby quasars, and extraordinarily difficult for an object this distant. Now picture the accretion disk, 7 light-years across. That number is almost impossible to visualize directly, so let me try to build it up from pieces. Light travels at approximately 300,000 kilometers per second. In 1 year, light travels about 9.5 trillion kilometers. 7 light-years is therefore about 66 trillion kilometers across. Our entire solar system, measured from the Sun to the outer edge of the Oort cloud, is perhaps 1 or 2 light-years in radius. The accretion disk of J0529-4351 could contain our entire solar system 3 or 4 times over, stacked side by side like coins on a table. Inside that disk, matter spirals inward toward the event horizon. The disk is not uniform. It is hottest and brightest in the inner regions, where matter is accelerating to significant fractions of the speed of light, and cooler and dimmer in the outer regions, where material is still settling into its inward trajectory. The inner disk emits radiation primarily in the X-ray and ultraviolet bands, photons energetic enough to ionize any atom they encounter. The outer disk emits radiation in the visible and infrared bands, longer wavelengths corresponding to cooler temperatures. The feeding rate of 1 solar mass per day means that somewhere in this system, matter equivalent to our entire Sun is crossing the event horizon every 24 hours. But the matter does not simply fall in like water down a drain. It spirals, it heats, it radiates. Before any parcel of gas reaches the event horizon, it has already given up a significant fraction of its mass energy as radiation. This is the source of the quasar's luminosity. The gravitational potential energy of infalling matter is converted to heat, and the heat is radiated away as light. The conversion efficiency of an accretion disk around a black hole can reach 40% or more. 40% of the rest mass energy of the infalling matter becomes radiation before the matter disappears behind the event horizon. Compare this to nuclear fusion in the core of a star, which converts less than 1% of rest mass energy to radiation. Accretion onto black holes is the most efficient sustained energy source known to physics, short of matter-antimatter annihilation. 500 trillion solar luminosities. Let that number sit for a moment. Our sun outputs approximately 382 septillion watts of power. Multiply that by 500 trillion, and you get a number so large that it loses meaning unless you anchor it to something comprehensible. Here is one anchor. The total power consumption of human civilization, all of it, every power plant and vehicle and device on Earth, is approximately 18 terawatts. J0529-4351 outputs, in 1 second, more energy than human civilization has consumed in its entire history, by a factor of trillions. If you could somehow capture and use the energy output of this quasar for a single second, you could power human civilization for longer than the universe has existed. Here is another anchor. The Milky Way galaxy contains roughly 200 billion stars. If you added up the light from all of them, the total luminosity would be in the tens of billions of solar luminosities. J0529-4351 is approximately 10,000 times more luminous than our entire galaxy. A single object, smaller in spatial extent than a typical globular cluster, outshines 100 billion stars. The violence of this place is difficult to convey. Christian Wolff called it the most violent place we know in the universe, and that assessment is not hyperbole. The inner regions of the accretion disk are bathed in radiation so intense that normal matter cannot exist there in any familiar form. Atoms are stripped of their electrons, leaving a plasma of bare nuclei and free electrons spiralling through magnetic fields of extraordinary strength. The temperatures near the inner edge of the disk reach millions of degrees, hot enough that the primary radiation is in the X-ray band. Photons energetic enough to penetrate flesh and ionize DNA. If a human observer could somehow be placed near the inner disk, they would be vaporized long before they could register any sensation, their atoms scattered and their constituent particles swept up in the inward spiral. And yet, from 12 billion light-years away, all of this violence is reduced to a faint smudge on a photographic plate, a point of light among billions of other points of light, a coordinate in a catalogue. The universe imposes perspective on us whether we want it or not. The most violent place we know looks from here like a dim star at the limit of visibility. The most luminous object ever found appears faint because distance dilutes everything, even 500 trillion suns. This is the strange truth about light in an expanding universe. It carries information across cosmic time, but it arrives weakened, stretched, diminished by the journey. The photons that left J0529-4351 when the universe was young arrive here carrying the same information they always carried, but their energy has been sapped by the expansion of space itself. Redshift is not merely a shift in colour, it is a shift in energy. Every photon that arrives from J0529-4351 has less energy than it had when it was emitted, because the universe has stretched during the photon's journey, and that stretching has lengthened the wavelength and lowered the frequency. The object that appears bright to us appeared far brighter to any observer who was closer, in space and in time, to the source. Imagine for a moment what J0529-4351 would have looked like from a planet in a nearby galaxy, one of those early galaxies that existed in the same cosmic epoch. From a distance of a few 100 million light-years, rather than 12 billion, the quasar would have been a beacon of astonishing intensity. It would have outshone the entire night sky of that hypothetical planet. It would have been visible in daylight, a second sun, a point of light so bright that it might have disrupted the cycles of any life that evolved there. The inhabitants of such a planet, if they had developed astronomy, would have had no difficulty identifying the object for what it was. It would have been obvious, unavoidable, terrifying in its brilliance. But we're not inhabitants of a nearby galaxy in that distant epoch. We are inhabitants of a galaxy 12 billion light-years away, and 12 billion years later. The light that reaches us is ancient and faint, and we must work to extract its secrets. We must build mirrors 27 feet across. We must integrate for hours. We must apply the tools of spectroscopy and photometry and statistical analysis to tease out the properties of an object that we will never visit, never observe up close, never study with anything other than the faint traces of light that happen to intersect our planet's location in space. This is the fundamental limitation of astronomy, and it is also the fundamental wonder of it. We are confined to a single planet in a single solar system, in a single galaxy, in a single corner of the observable universe. We cannot travel to the objects we study. We cannot send probes to quasars, or wander among the stars of distant galaxies, or take direct measurements of black hole accretion disks. We have only light. Photons that left their sources millions or billions of years ago traversed the expanding void and happened to arrive at the precise location where a telescope was waiting. From those photons, we reconstruct the universe. The reconstruction is never complete. It cannot be complete because we are always working with incomplete information. We see the light that reaches us, but we do not see the light that travels in other directions. We see the wavelength that our detectors can register, but we miss the wavelengths that our instruments are blind to. We see the moments when we happen to be observing, but we miss the moments when our telescopes are pointed elsewhere, or when the object is below the horizon, or when clouds block the view. The image of the universe that we construct from astronomical observations is a patchwork, a mosaic assembled from fragments of information gathered over decades and centuries. And within that mosaic, objects like J0529-4351 are the pieces that do not quite fit. They are the tiles of a different colour, the shapes that break the pattern, the anomalies that force us to revise our understanding of what the mosaic depicts. For 40 years, this particular tile was misplaced. It sat in the wrong part of the picture, labelled as something it was not. The pattern looked complete without it, or complete enough that no one noticed the discrepancy. And then someone looked again, and the tile moved to its proper place, and the entire picture shifted slightly to accommodate it. How many other tiles are misplaced? We cannot know. That is the honest answer. We cannot audit every object in every catalogue. We cannot re-examine every classification decision made by every automated system. The scale of modern astronomical archives makes comprehensive review impossible. What we can do is look for patterns of error. We can ask which categories of objects are most likely to be misclassified. We can identify the boundary regions where automated systems have low confidence. We can apply human judgment to the places where human judgment is most needed. This is the work that lies ahead. Not just for quasars, but for every class of object that might be hiding in the archives. Gravitational wave sources, fast radio bursts, kilonovae, rogue planets, free-floating black holes, primordial structures from the earliest epochs of galaxy formation. Each category has its own signatures, its own potential for confusion with other types of objects, its own set of assumptions that might be too narrow. Each category represents a population that may be larger and stranger than our current models suggest. The teams that discovered J0529-4351 understood this. They were not looking for a single extraordinary object. They were looking for a method, a way of identifying misclassified quasars in existing archives. The discovery of the most luminous object ever found was in a sense a bonus. A spectacular bonus, to be sure, but incidental to the larger project of improving our classification systems and finding the objects that those systems have missed. That method is now being applied more broadly. Other teams are developing similar approaches, using machine learning not to classify objects directly, but to identify objects that deserve closer inspection. The algorithms are being trained not on what objects are, but on what objects might be wrong. This is a subtle but important shift. The question changes from "what is this?" to "should we check this again?" The second question is in many ways more valuable, because it acknowledges the limits of the system asking the question. The night sky remains. After all our discoveries, after all our surveys and catalogues and classifications, the night sky remains what it has always been, a field of light carrying messages we have not yet decoded. Some of those messages are from nearby stars, familiar and well understood, their spectra documented and their distances measured to high precision. Some of those messages are from distant galaxies, faint smudges that reveal themselves only in long exposure photographs, their individual stars too dim to see. And some of those messages are from objects we have not yet learned to recognize, objects wearing disguises that our current instruments cannot penetrate, objects waiting for the next generation of telescopes or the next insight from a graduate student who notices something that does not quite fit. 12 billion years of patience. That is how long J0529-4351 waited for us to recognize it. The light left the quasar when the universe was young, travelled through expanding space as galaxies formed and stars were born and died, and civilizations rose and fell on countless worlds, and finally arrived at Earth just in time to be misclassified by an automated system and filed away in an archive where it sat for 4 decades. The quasar did not care. Objects do not care. They simply exist, radiating their energy into the void, indifferent to whether anyone is watching or whether anyone understands. We are the ones who care. We are the ones who build telescopes and write algorithms and check the data that does not fit. We are the ones who look up at the night sky and ask what is out there, what we have missed, what remains to be discovered. The universe does not owe us answers. It does not arrange itself for our convenience. It does not label its objects or sort them into neat categories. It simply is, vast and strange and filled with things we have not yet imagined. The most luminous object ever discovered was hidden in plain sight for 40 years. That sentence should make us humble. It should make us wonder what else is hidden, what other records remain to be broken, what other assumptions remain to be overturned. The archives are deep and the sky is wide and the universe is older and larger than human intuition can grasp. Somewhere in that vastness there are objects waiting. Black holes more massive than J0529-4351. Quasars more luminous. Structures more extreme. Anomalies that will force us to revise our theories and expand our categories and redraw our maps of what exists. The search continues. The checking never ends. And the next discovery is already out there, patient and indifferent, waiting for someone to notice that something does not quite look right. The search continues. But let us pause here, at the edge of what we know, and ask a different kind of question. Not what else is out there, but what this particular discovery tells us about the nature of knowledge itself, about the relationship between seeing and understanding, about the strange position we occupy as conscious beings trying to comprehend a universe that was not made for comprehension. J0529-4351 is not just an astronomical curiosity. It is a philosophical provocation. Consider what it means for an object to be hidden in plain sight. The phrase itself contains a paradox. Plain sight suggests visibility, accessibility, the absence of concealment. Hidden suggests the opposite. Yet both conditions applied simultaneously to the same object for 4 decades. The quasar was visible in every sense that matters astronomically. Its light reached our instruments. Its photons were captured on photographic plates and later on digital sensors. Its position was recorded in catalogues that anyone could access. There was no physical barrier between the quasar and our awareness of it. The barrier was conceptual. The barrier was inside our systems of classification, our assumptions about what kind of objects produce what kind of signals, our unexamined certainty that something so bright must be something familiar. The universe showed us the truth. We did not see it, not because our eyes were closed, but because our minds had already decided what they were looking at. This is not a failure unique to astronomy. It is a pattern that runs through the entire history of human knowledge. We see what we expect to see. We categorize before we investigate. We trust our systems more than we trust anomalies, and so anomalies become invisible even when they are staring directly at us. The most famous examples come from science, but the same dynamic operates in medicine, in economics, in politics, in everyday perception. We are not blank slates receiving information from the world. We are active interpreters, and our interpretations are shaped by frameworks that predate the data. J0529-4351 was discovered not by gathering new data, but by questioning old interpretations. The photons had been collected decades ago. The measurements were already in the archives. What was missing was doubt. What was missing was someone willing to ask whether the classification might be wrong, whether the brightness that seemed to confirm a familiar identification might instead indicate something unprecedented. This is perhaps the deepest lesson the quasar has to teach us. Not about black holes or accretion disks or the physics of the early universe, though it teaches us about all of those things. The deepest lesson is about the structure of discovery itself. Progress does not always require new instruments or new observations. Sometimes it requires only the willingness to revisit what we thought we already knew and ask whether we were certain for the right reasons. The history of science is filled with such reversals, objects that were dismissed as uninteresting and later revealed to be revolutionary, signals that were filtered out as noise and later recognized as messages, patterns that were ignored for generations until someone with fresh eyes noticed what had been visible all along. The cosmic microwave background was initially mistaken for antenna interference. Pulsars were briefly thought to be signals from extraterrestrial civilizations before their natural origin was understood. The expansion of the universe was hidden in data that multiple astronomers had collected without recognizing its significance. In each case, the critical discovery was not the gathering of new evidence, but the reinterpretation of existing evidence through a different conceptual lens. J0529-4351 belongs to this tradition. The quasar did not change. The light did not change. What changed was our willingness to question whether we had understood correctly in the first place. And here we arrive at something uncomfortable. If the most luminous object in the universe could hide in our archives for 40 years, what else might be hiding? Not just in astronomical databases, but in all the vast stores of information that humanity has accumulated. We live in an age of data abundance unprecedented in human history. Sensors and satellites and instruments of every kind are collecting measurements at rates that no human mind could process. Algorithms sort and classify and categorize this flood of information, applying rules that were written by humans but that operate at scales beyond human comprehension. We trust these systems because we must. No alternative exists. The data is too vast for any other approach. But J0529-4351 reminds us that trust has limits. The systems are doing what they were designed to do, and what they were designed to do is apply existing categories to new data. They are not designed to question those categories. They are not designed to notice when an object does not fit, or to flag their own uncertainty, or to wonder whether the framework itself might be inadequate. The algorithms are powerful but not wise. They can process information at speeds no human could match, but they cannot step back and ask whether they are asking the right questions. That capacity belongs to us. To the graduate students who notice anomalies, to the researchers who develop methods for checking uncertain classifications, to the scientists who maintain enough humility to wonder whether their predecessors might have been wrong. This is not a task that can be fully automated. It requires the very human willingness to doubt, to question, to look again at something everyone assumed was settled. The discovery of J0529-4351 was, in this sense, a triumph of human curiosity over algorithmic certainty. The machines had classified it. The humans checked. The humans were right to check, and the machines were wrong in their classification, and now we know something about the universe that we did not know before. This should be celebrated, but it should also be sobering. How many checks are not performed? How many objects remain misclassified because no one has the time or the funding or the inclination to revisit old data? The archives grow larger every year. The fraction of that data that receives careful human scrutiny grows smaller. The potential for hidden discoveries increases even as our ability to find them is stretched thin. FOS29-4351 got lucky, if luck is the right word for an object that has no consciousness and no stake in being discovered. The right people happen to develop the right methods at the right time, and happen to apply those methods to a region of sky that happened to contain an object spectacular enough to rewrite the record books. But for every J0529-4351 that is found, how many objects of equal importance remain buried? How many revolutionary discoveries are sitting in databases right now waiting for someone to notice that the classification does not quite fit? We do not know. We cannot know. That is precisely the problem. Let this sit for a moment. The most luminous object ever discovered was visible for 4 decades before anyone recognized what it was. This was not because the technology did not exist to find it. This was not because the data was inaccessible or the instruments were inadequate. This was purely a failure of interpretation, of conceptual frameworks, of the assumptions that shape what we see even when we are looking directly at it. And now think about what this means for everything else we think we know. The classification of objects in astronomical catalogues is one of the most rigorous and well-documented systems of categorization that humans have ever created. Thousands of astronomers over more than a century have contributed to developing and refining these systems. The criteria are explicit. The methods are published. The data is available for independent verification. If a misclassification this significant could persist for this long in such a carefully constructed system, what does that suggest about systems that are less rigorous, about categories that are more subjective, about frameworks where the criteria are unexamined and the assumptions are hidden? The quasar is not just an astronomical discovery. It is a warning, a reminder that our systems of knowledge, no matter how sophisticated, are built on foundations of assumption that may be wrong in ways we have not yet imagined. The universe is under no obligation to fit our categories. It will continue to present objects that defy classification, signals that do not match expectations, phenomena that expose the limits of our understanding. Our choice is whether to notice these anomalies or to filter them away as noise. J0529-4351 was almost filtered away. For 40 years, it was filtered away. Only persistence and doubt and the willingness to question brought it back. Now bring your attention back to the object itself. We have spent so much time discussing the implications of its discovery that we might lose sight of what was actually found. Let us return to the quasar and feel its weight one more time. 17 billion solar masses compressed into a region smaller than our solar system. That is the black hole at the heart of J0529-4351. 17 billion suns worth of matter, concentrated so densely that space itself curves back on itself and nothing, not even light, can escape once it crosses the event horizon. This is not metaphor. This is geometry. The black hole is literally a region of space-time from which there is no exit, a permanent removal from the accessible universe, a boundary beyond which physical law as we understand it ceases to make predictions. Around this boundary, matter spirals inward. The accretion disk stretches 7 light-years across, a rotating plane of gas and dust heated to temperatures that exceed the cores of stars. Material falls toward the black hole at velocities approaching significant fractions of the speed of light. Friction within the disk converts gravitational energy into radiation with an efficiency that exceeds any process known to physics, except matter-antimatter annihilation. The result is a luminosity so extreme that it outshines everything else in the observable universe. 500 trillion suns. That number has appeared before in this account, but say it once more, slowly. 500 trillion. 5 with 14 zeros after it. Every second, the quasar releases more energy than our sun will release in its entire 10 billion year lifetime. Every second. And it has been doing this for millions of years at minimum. The violence is almost impossible to convey. The accretion disk is not smooth and stable. It is turbulent, chaotic, racked by magnetic field lines that tangle and snap and release bursts of energy that would sterilize entire solar systems. Jets of material erupt from the poles of the black hole, accelerated to velocities so close to the speed of light that relativistic effects become dominant. These jets can extend for hundreds of thousands of light-years, far beyond the galaxy that hosts the quasar, carving paths through intergalactic space and depositing energy into the cosmic web that connects clusters of galaxies. The quasar is not just an object. It is a process, an ongoing catastrophe, a transformation of matter into energy on scales that dwarf everything else in nature. And it is 12 billion light-years away. The light we see today left the quasar when the universe was less than 2 billion years old. Galaxies were still assembling from the primordial gas left over from the Big Bang. The Milky Way did not yet exist in its current form. Our sun would not ignite for another 8 billion years. Earth would not form for almost 9 billion years. Life would not appear on our planet for almost 10 billion years. Human beings would not evolve for almost 12 billion years. And throughout all of that time, the light from J0529-4351 was travelling through space, crossing distances so vast that the universe itself expanded measurably during the journey, finally arriving at Earth to be captured by photographic plates and misclassified as a star. The quasar itself is almost certainly gone. 12 billion years is longer than any quasar phase has ever been observed to last. The black hole remains. Black holes do not disappear except through the excruciatingly slow process of Hawking radiation, which would take timescales vastly longer than the current age of the universe. But the feeding frenzy that produced the luminosity has almost certainly ended. The gas has been consumed or expelled. The accretion disk has faded. The galaxy that hosted the quasar has evolved into something more sedate. Perhaps an ordinary elliptical galaxy with a dormant black hole at its centre, no longer blazing with the fury of its youth. What we see is a ghost, a record of an event that ended before the Earth existed. We cannot observe the quasar as it is now because that information has not yet reached us. It will take another 12 billion years for light leaving the quasar today to arrive here, and by then the Sun will have exhausted its hydrogen, expanded into a red giant and engulfed the inner planets. The future state of J0529-4351 is information that will never be available to any observer on Earth. We are limited to this single snapshot, this frozen image of violence and luminosity from the youth of the cosmos. And yet this snapshot tells us so much. It tells us that supermassive black holes could grow to enormous sizes very early in cosmic history. It tells us that the conditions for extreme accretion existed when the universe was less than 2 billion years old. It tells us that the processes generating quasar luminosity were already operating at maximum intensity, pushing against the theoretical limits of how much energy can be extracted from infalling matter. The quasar is data. It is a measurement of what was possible in the early universe, and that measurement challenges our models. The problem is time. A black hole of 17 billion solar masses cannot form instantaneously. It must grow, accumulating matter over millions or billions of years. But the universe was less than 2 billion years old when the light we see left the quasar. How did a black hole grow so massive so quickly? The standard scenarios, collapse of massive stars, gradual accretion of gas, struggle to produce objects this large in the time available. Something unusual must have happened. Perhaps the black hole formed from the direct collapse of an enormous cloud of gas, bypassing the stellar stage entirely. Perhaps mergers with other black holes accelerated its growth. Perhaps accretion rates exceeded what our models consider typical. We do not know. J0529-4351 is not just a record, it is a puzzle. The discovery adds urgency to questions that astronomers have been asking for decades. How did the first black holes form? What conditions allowed them to grow so rapidly? Why do some galaxies host quasars while others do not? How does the presence of a supermassive black hole affect the evolution of its host galaxy? These questions have implications that extend beyond astronomy into cosmology, into the study of how structure formed in the early universe, into the fundamental physics of gravity and matter under extreme conditions. J0529-4351 will not answer all of these questions. No single object could. But it provides a data point at the extreme edge of parameter space, a measurement of what is possible, a constraint on any theory that attempts to explain how the universe came to look the way it does. That data point was invisible for 40 years. It is visible now, and the theorists will have to account for it. Let the weight of this settle. The most luminous object ever discovered, a black hole larger than most galaxy centres, an accretion disk that would span from the Sun to the nearest stars, a luminosity that exceeds everything else we have ever measured, hidden in plain sight, misclassified as ordinary, waiting in the archives until someone thought to check. This is the universe we live in, a universe that does not reveal itself easily, a universe filled with objects that exceed our imagination, lurking at distances so vast that their light is older than our planet. A universe that will humble any certainty and punish any complacency and reward only the persistent willingness to ask whether what we think we know might be wrong. The night sky looks quiet from here, a scattering of points, some bright, some faint, all seemingly peaceful. But that peace is an illusion of distance. Those points are furnaces and explosions and collisions and collapses, violence rendered silent by the intervening void. The light arrives gently, diminished by billions of years of travel, carrying news of cataclysms that ended before life existed on Earth. We receive this light as information, we classify it, we file it in archives, and sometimes, if we are careful and humble and willing to doubt, we recognize that what we thought we understood was only the beginning. J0529-4351 was discovered because someone noticed something did not fit. That is the entire story. That is the only story that ever matters in science. The willingness to look again at what everyone else assumed was settled. The stubbornness that refuses to accept a classification just because a system assigned it. The curiosity that asks not, what is this, but should we check this again? There will be other discoveries. There will be objects more luminous, black holes more massive, phenomena more extreme. The universe is vast beyond comprehension and strange beyond imagination, and we have only begun to explore it. Every instrument we build reveals new mysteries. Every survey we conduct finds objects that challenge our theories. The frontier does not recede, it expands. The more we learn, the more we discover that we have not yet learned, and the archive of questions grows faster than the archive of answers. But tonight, at this moment, let J0529-4351 stand as a representative of everything out there that we have not yet recognized. A symbol of hidden knowledge. A reminder that visibility is not the same as understanding. A warning against the comfortable assumption that our categories capture reality. 500 trillion suns, 7 light years across, 17 billion solar masses, 12 billion years of travel, 40 years of waiting, 1 moment of recognition. The light arrived, the systems classified it, the humans checked. The universe, as always, was stranger than expected. And somewhere out there, in the archives we have not yet searched and the catalogues we have not yet questioned, the next discovery is waiting. Patient, indifferent, hidden in plain sight. The checking never ends.